Okay, so last video we continued to solve our improper integration problem, and we found that we had to use integration by parts to solve the integral that resulted from using the definition of improper integration. So that expression, by using the definition of improper integration, resulted in this. So we have one integral and one expression that we can evaluate. Looking at the integral, we can see that it's in the similar form as our original here, except instead of a sign we have a cosine. We can see that the two negatives will cancel out, so it's the exact same except for the cosine. So it implies that we're going to use integration by parts again. If we were to go through the list of integration tools, integration by parts would come out as the superb answer. Why? Because if we were to differentiate cosine again, we would get a sine, and that would leave us with the same expression as before, and we would be able to isolate for the expression on both sides of the equation and solve what our integral is. So that seems like the game plan. So right now we have this integral. We will use integration by parts again. So set up our parameters, v equaling the same thing, dv over dx being the same thing, e to the minus e to the minus x, and then our u in this case is going to equal to sine x, because our du is equal to cos x dx, as we can see in the problem. So subbing this back into the integration by parts formula, we get our integral of uv minus integral of u dv, and that will give us sine x e to the minus x minus e to the minus x. Yeah, this is from, oh, excuse me, there's no integral here, that's my bad, let me take that out. Okay, so sine x e to the minus x from 0 to t minus our integral of sine x minus e to the minus x dx. Okay, so our minus signs will cancel out, and this integral here equals sine x e to the minus x 0 to t. The minus sign cancels out, so plus integral of sine x e to the minus x dx. And look at that, we have the same expression here as we had in the original. So why don't we set that equal to I is equal to our integral of 0 to t sine x e to the minus x dx, giving us I is equal to our minus cosine x e to the minus x 0 to t minus this integral here, which we found to be this whole expression. So that's going to be our minus sine x e to the minus x 0 to t plus integral of, which is plus our I. Yeah, so transpose distributing the negative sign, we will get a minus I here. So when we take it here, we get plus I. So we get 2I is going to equal to our minus cos x e to the minus x 0 to t minus sine x e to the minus x t. So that implies I is equal to 1/2 minus cos x e to the minus x 0 to t minus sine x e to the minus x 0 to t. Okay, so expanding our or evaluating the results of the integral, we get a 1/2 minus cos. The t will sub in, so cos t e to the minus t minus cosine at 0, and e to the minus x at 0 is just 1, so we get minus 1. So this will be I equal to minus 1/2 minus cos at t e to the minus t, and then this is going to be our minus cosine at 0 is 1, e to the minus x at 0 is 1, so minus 1. And then we get minus, so this is 0 to t again, so minus sine at t e to the minus t, and then minus sine at 0 is 0, so we get a minus 0 because 0 multiplied by anything is 0. So that leaves our I is equal to, cleaning this up, we get a 1/2 minus e to the minus t cos at t plus sine at t, and this minus 1 is plus 1, so plus 1. So this is the expression for our integral, and we will continue taking on the limit and finally solving the problem in the next video.